Now we're going back to our pre-calculus textbook to look at how to utilize the operations we've been reviewing for the last few days. So in this section, we're focusing on how to use the operations on rational expressions to solve a rational equation. And we're going to do this both algebraically and from looking at the graph. So first, the algebra operations behind this. Your very first step should be to factor the denominators so that you can find what is the least common denominator between all of the fractions you have. Now, sometimes there may not be any factoring to do, in which case you can just completely skip this step. But if you look at the bottom of the fractions and you see some factoring, make sure you do that first so that it's easier to find the LCD of all the fractions. Next, you're going to multiply every single term by whatever the LCD is. That way it's going to clear all of your fractions out. If you still have a fraction after this step 2, then you must not have found the LCD correctly because there shouldn't be any fractions left after performing this operation. Then you're going to go through and do any operations you see left. Since the fractions are cleared out, you should be able to do some more distributing or simplifying, combining like terms, etc., so that you can set up moving all the variables to one side of the equation and solving from there. Now, there is an extra complication that comes in from these rational equations that we need to go over. There's something that is an extraneous solution. This is introduced when you multiply both sides of the fraction by a variable. So since we multiplied both sides of the equation by some kind of an x term, it may have created a fake answer. That's basically what this is. So you may want to add that into your notes. An extraneous solution is basically a fake answer. So we need to figure out whether it's a real solution or not. And we're going to do that by plugging the numbers you found back into the original equation and seeing if any of them give you an undefined value. If it's undefined, then it must have been an extraneous solution, so we will not include it as a final answer. If you can plug it into the equation just fine and it doesn't cause anything like a 0 on the bottom of a fraction, then the answer is fine, so you would include it as one of your final answers. So here's our first example. You can see that we have several rational terms, and it's an equation because we have this equal symbol here. There isn't any factoring that I can do in any of these fractions separately. Everything is as factored as possible, so I just need to identify what the least common denominator is. Well, I see everything has at least a single x in it, and I see everything has a 2 or a 5 in it. So 2 times 5 in this case is 10. So the smallest common denominator I can use is 10x. That's what I will multiply by every single one of the terms that I see here. Now, when I multiply 10x by the first term, the x's on top and bottom would cancel, 10x times 1 over x. So then all I'm going to be left with is 10. When I come to this next term, 10x times 1 over 5, or 10x over 5, the 10 and the 5 will reduce, so that's just equal to 2, but the x's didn't cancel, so I still have an x. And then for this last term, if I multiply by 10x over 1, you'll end up with, in fact, let me even write this one on the side just so that you guys can see exactly what I'm doing. 3 over 2x, I said we're multiplying everything by 10x, which means 10x over 1. So in this case, I'm noticing that the x's will cancel, and the 10 over 2 can be reduced as well. You can think of that as just 5 over 1 instead. So 5 times 3 is equal to positive 15. So at this point, you need to do any other distributing, combining like terms, anything else that's required, but I don't really have anything left here that I need to combine. I can just go on to the solving step. So in this case, since I just have an x, I'm going to subtract the 15 to the opposite side and make this negative 5. And then divide both sides by 2. So my answer is negative 5 halves. So my solution appears to be negative 5 halves, but since I did earlier in the solution multiply both sides of the equation by an x, if you multiply everything by an x, you could have created a fake answer. So I'm going to check to see if plugging in negative 5 halves into any of these x values would have caused a problem. Because remember, I don't want to end up dividing by 0. Well, if I plug negative 5 halves into this, then the denominator is not equal to 0. It's equal to negative 5 halves. If I plug negative 5 halves into this, when you multiply by 2, you end up with a negative 5 in the bottom. So again, that's not undefined either. So this is a valid solution. It is not extraneous because plugging it in does not cause any of those situations we have to avoid, like dividing by 0. Here I have a much more complicated example. The first step I gave you guys was to factor any of the denominators you see. And although these two fractions, the denominators are just fine, x plus 1 and x plus 2 are as factored as can be, this other denominator is a trinomial, so I need to see if there are two numbers that multiply together to equal 2, but add up to equal 3. So in this case, my factoring, I should be getting plus 2 and plus 1. The order doesn't matter on that for factoring. So this fraction did have a denominator I could factor, so I'm going to think of this instead as x minus 1 over x plus 1 times x plus 2. The other ones are already factored, and now I can see what my LCD is. This first one has an x plus 1 factor and an x plus 2 factor. This one has an x plus 2, so it's just missing x plus 1. This one has an x plus 1, so it's just missing the x plus 2. So in fact, my LCD is x plus 1 times x plus 2. If I multiply everything by these two factors, it will clear out all of my fractions. So when I multiply my LCD by the first fraction, well, I have an x plus 1 and an x plus 2 in the bottom. That'll cancel the x plus 1 and the x plus 2 that I'm multiplying by. So all that's going to be left is the top, x minus 1. Then I come to the next piece. I'm going to multiply this second fraction by x plus 1 and x plus 2. When I multiply by x plus 2, that'll cancel out what's in the denominator, but the x plus 1 will not be canceled. So I'm going to be left with the 2x that's already on top and the extra x plus 1 that I'm multiplying by. Remember, I'm multiplying by both of these things, but in this case, the x plus 2 is canceling with what I have in the bottom. So now I need to multiply my two factors by the last fraction. So in this case, I have an x plus 1 in the bottom. When I multiply by an x plus 1 on top, the x plus 1s will cancel. So for this last fraction, I'm going to be left with the part that's on top, x minus 1, and the other factor I'm multiplying by, the one that doesn't cancel out, the x plus 2. So that was my step of multiplying everything by the LCD. I had to multiply it by all three of my fractions, my three different terms here. Well, this time, unlike the last example I did, you can see that there is a little bit of distributing I can perform. The x minus 1 is fine as it is, but here I have 2x times x, and I have a 2x times 1. On the other side of the equation, I can distribute this out. X times x, x times 2, negative 1 times x, and negative 1 times positive 2. To solve this equation, since I do have x squared terms in it, I need to move everything to one side. So I'm going to subtract x squared from both sides. So I'll have 2x squared minus x squared, which is x squared. Now on the left-hand side, I have a positive x plus 2 more x. Those are like terms. So that would be 3x. But I need to bring these over. So I have 3x on the left, and I have 1x on the right, because 2x minus x is x. So when I move the x over, it's going to be 3x minus x, which is 2x. And then for the constants, I have a negative 1 on the left and a negative 2 on the right. So when I add 2 to the other side, I'm going to end up with a plus 1. Now sometimes you may end up with something here that you have to use a quadratic formula on. If you can't figure out how to factor it, that should be your go-to. In this case, I'm going to see if I can factor this, because the two numbers that would multiply together to equal 1, but add up to give me 2, that would be x plus 1 and x plus 1, which is x plus 1 squared. So I'm going to bring this over and keep solving. The opposite of squaring is taking the square root of both sides of the equation. And usually you get a plus or minus answer for that, but since there is no positive or negative 0, it's just 0, I don't need to worry about the positive and negative in this case. And then I would subtract 1 to the other side of the equation, so I end up with x is equal to negative 1. Now, if you stopped there and you circled that, you'd be really close to having the correct answer, but there's one thing you have to keep in mind. Make sure you take the answers you get and you try to plug them back into the original equation that you had. We're looking for anything that might be undefined, like the 0 in the bottom of a fraction or a negative inside of a radical. And if I try to plug negative 1 into this fraction right here in particular, Plugging in -1 and then adding 1 would give me a 0 in the bottom of this fraction. It doesn't matter that it makes all of the fractions 0. It doesn't make this one 0. The fact that it makes any of them have a denominator of 0 means that this is actually an extraneous solution. This is an extraneous solution. So if they ask you what are the real solutions, or if they just say what are the solutions, you would actually leave this one off. You would not include it as a final answer. So since I don't have any final answers in this case, my solution is that there is none. It would be no solution would be my final answer. If they do specify that they want to know what the extraneous solutions are, then I would specify that x equals -1 is extraneous, because it does not work in the original equation. It's not a real answer since it's actually undefined for that value. So here's the last concept we're going to look at here. Solving them graphically is a much easier process. If you are either given the graph, or if they give you a complicated equation, you can just plug it into Desmos or use a graphing calculator to draw the image. But basically, when you are trying to find the solutions from a graph, you're just trying to identify where does the graph touch the x-axis. So in this one, you can see that there are two locations. There's at x equals 1, and there's another one over here at x equals 6. So they may give you a couple examples. They may say, is x equals 1 a solution? From looking at this, you would say yes. Is x equals 6 a solution? You would say yes. If they mention any other number, like if they say, is x equals 3 a solution? I do not see the graph touching the x-axis at 3. So if that's one of the solutions they ask me about, from looking at this graph, I would have to say, no, that must have been an extraneous solution because the graph is not actually touching that at that x value. So basically, any x values they give you, if you see the graph touching the x-axis there, it's a real solution. If you don't see the graph touching the x-axis at those values, then it must be an extraneous solution. So there will be a couple examples like that in the textbook. And that should be it for this section. So I hope that'll be helpful for you guys on the textbook and math lab assignments.